Hello, Algebra 2 Advanced. This video lesson about Chapter 3.4 focuses on a topic called linear programming. There are 5 things out of this section of the textbook that I expect you to know for our next exam. I'm going to ask you to hit the pause button and read these things to yourself, and then I'll move on. Okay, I'm going to assume that you read these 5 items, and I think as you'll see as we go through the video, I'm going to touch on each of the 5 points. First of all, what is linear programming? Well, it's basically a graphing technique, and you use it when you want to find your best choice among a variety of options. Usually this is going to be your maximum choice. For example, you might want to maximize the amount of revenue that you're going to make from some various options you have about how you would make revenue. Or you might want to maximize the number of lives you want to save in some sort of action that you might want to take, or you might want to maximize the usefulness of your workers in some sort of project. It can, however, be used to find minimum values, and in fact we'll talk about that briefly during this video, and there may be some times when minimum is exactly what you want. A little bit of history. George Dantzig, called the father of linear programming, was a gentleman who came up with much of the thinking behind it. His theories were kept secret during World War II because they were considered strategic advantage, and in particular he looked at, as I say here, how best to assign 50 tasks across 50 different employees to get the maximum value out of each of the employees. Other types of topics that were used during the war focused on the fact that there were limits on various resources, workers, steel, and etc., and how best to make use of those limited resources is exactly where linear programming really comes in to be of great value. All right, so let's look at how you do it. First of all, when do you know that you even have a linear programming problem? You know that you do when you want to maximize something among a variety of different options. So in this word problem down here, go ahead and hit the pause button, and when you come back, I'm going to talk about it. Okay, I'm going to assume that you read this paragraph about the bakery. You know that you want to maximize profits. So this is a linear programming problem. Step 2 then is to find something called your objective function. The objective function, as I say here, is always going to be the maximized thing. The maximized item is equal to. So in this case, what you want to maximize is profit. So your objective function is going to be written as profit is equal to. And you always start off a linear programming problem once you realize that it is something that you want to maximize or minimize by saying, what is it that I want to maximize? And set that equal to its ingredients. Well, the ingredients for profit are $35 in profit from each batch of bread and $10 in profit for each batch of muffins. Simplifying these to make it look more like an algebraic equation, I've got 35 times B. B stands for batches of bread, and M for batches of muffins. You're going to have to be careful sometimes, like in this problem where I've got B that could be attributed to batches or to bread in how you pick your letters. Third step then is you're going to make a table of constraints, the things that keep you from reaching that maximum in any direction that you'd like to take and steer you toward one particular direction. So in doing that, the first thing that you do to make that table is you're going to have column headings for the table, and the column headings are going to be the ingredients of that objective function. Well, remember, the objective function was this, 35b plus 10m, so B and M are going to be the headings of your table. Batches of bread and batches of muffins. Sometimes it makes more sense to write the words out than simply the letters because you can lose track of what those letters stand for. The next step is these row labels. You've got to identify the things that are constraining you. And the 2 things that are constraining you from baking as much of everything as you could possibly want are the facts that you've got limits on prep time and on baking time. And those are identified here. You then can plug in the values to fill out this table. It takes 4 hours to prepare and 1 hour to bake the bread. It takes half an hour to prepare and half an hour to bake the muffins. So filling those in, you're now ready for this last column that I mentioned here. You've got to add a final column for your limits. And what are those limits? Well, I said before, there's a limit on prep time. The maximum prep time available is 16 hours, so it's a less than or equal to. And the maximum baking time is 10 hours, again, less than or equal to. These now are going to become inequalities. that you're going to work with. Your next step is going to be to graph those inequalities from your table. Here's that table that we just made together. So really what I have here is 4b plus 0.5m is less than or equal to 16. And similarly, I've got 1b plus 0.5m is less than or equal to 10. And I have to graph these. When I label these axes, again, I'm going to use those ingredients from the objective function, the b and the m. I recommend that you stay consistent all the way through. The first variable you picked for your objective function should be the first column in your table, and it should be the x-axis when you make the graph. That way you won't get yourself confused and mix up the two choices and actually make the opposite recommendation of what you should have. So I've got bread on the x-axis and m on the y, just like x comes before y in a table or in coordinate points. The next thing I'm going to notice, if I tried to graph this inequality, which was, after all, I said 4b plus 0.5m is less than or equal to 16, it's easy to graph the b intercept. 16 divided by 4 is 4, and I would place that here. But the problem I'm going to have is when it comes time to graph the m intercept. 16 divided by 0.5 is 32. And originally I only had from 0 to 10, so I had to adjust my scale on the left here. Now that I've got that so that 32 will clearly fit, I can go ahead and graph these inequalities. Again, the one that I've now marked orange is 4b plus 0.5m is less than or equal to 16, and then I've marked the second one in purple. Here are those two boundary lines. Again, the orange standing for this story here about prep time, and the purple standing for this story here about baking time. Once I've got the boundary lines of the inequalities, I remind myself, after all, they are inequalities, which means that I've got to take account of the fact that I've got a less than or equal to situation in both of these. So they're both pinching inward. The common area between these two inequalities is this region right here. Both purple is pinching in and orange is pinching in. So that would be the area that I would shade. Now, here comes the insight that Danzig and others who founded linear programming came up with. Your maximum and minimum choices are always at one of the corner points. So what do I mean by the corner points? I mean these corners of this shaded area, and there are 4 of them because this is a 4-sided shape that I've shaded here. That will always be true. May not seem like a great insight now that you see it, but back before it was recognized, back as I say, when Danzig was looking at trying to figure out how do I maximize the usefulness of 50 people when I've got 50 different tasks that I might assign them to. In his case, he had 50 different lines that he was graphing, and he was trying to find what the best options were. There were infinite options, actually, in that kind of situation. But once he was able to graph it and recognize that the corner points always revealed best choices, he had a limited number that he had to pick between, and it went a lot faster. Okay, so now my choices are going to be at these corners. The coordinates for those, whoops, didn't mean to move that. Excuse me. Hang on a second, let me put that back where it was there. The choices are these 4 points, 0, 20, 2, 16, 4, 0, and 0, 0. What they stand for is 0 batches of bread and 20 batches of muffins. And similarly down here, 4 batches of bread and 0 batches of muffins. So I simply plug those coordinates, as this says, into my objective function. So I rewrite this objective function 4 times with space for the 4 sets of coordinates, plug those values in, simply calculate what's 35 times 0, that's 0, plus 10 times 20 is 200. So my first choice would come up with $200, but my best choice turns out to be this second choice here, where I come out with $230. That's the largest amount I could possibly get in the scenario that I've described here. So my best choice is to make 2 batches of bread and 16 batches of muffins. That's how linear programming works. So now let me give you a chance to use one. Here's a paragraph. Hit the pause button, read that to yourself, and then see if you can figure out what the objective function is. Okay, I'm going to assume that you've read it and you've at least thought of the objective function. In this case, what you're trying to do is maximize profit. So your formula for profit is going to be $3 times every, pound, I guess it is, of alphabets, plus $4 for every pound of honeycomb. Now your second task is to make a table of constraints. Again, hit the pause button, and when you come back, I'll show you the table of constraints for this story about the two types of cereal. Okay, I'm going to assume that you did that. Here is that table. The things that are constraining me are rice and corn. The limits on the amount of rice and corn that I can have, well, it says in the very first sentence this time, I've got 6 bushels of rice, so that's got to be less than or equal to 6 on the rice, and similarly 6 bushels of corn, so it's got to be less than or equal to 6 on the corn. Hit the pause button and make sure you understand this table if you didn't create it yourself, and when you come back, we're going to move on to the next task. Okay, I'm going to assume that you did that. The next task is to draw the graph now. So go ahead, based on this table, and draw that graph, and when you come back, I'll show you my version. All right, I'm going to assume that you did that. And here's my version of the graph of the story about honeycomb and alphabets. Remember, keeping consistent here, I've got A first in the objective function. I've got A as the first column in the table. Similarly, I've got A for alphabets on the x-axis of my graph. The green line, I've said, is this story about the corn limit, and the red line, I've said, is the story about the rice limit. And based on what I've drawn here, I've got 4 corners. I haven't bothered this time to shade it in, but this is the area here that's in common among the two inequalities, and those blue circles indicate the 4 corners of that 4-sided shape. Now comes the last task. Decide which of those corner points is the one that I should choose. Go ahead and hit your pause button, and when you come back, I'll show you the answer. Okay, I'm going to assume that you did that. There are the values, oops, I did it again, didn't mean to move that. There are the values at each of the 4 corners. I've plugged those values in here into the objective function. And now, doing the arithmetic work out, I find that my first choice here, this first corner, would have given me $12, but this second corner here would have given me 14, and I never have an option that goes higher than 14. 14 is my best choice, and in that case, what I need are 2, I guess it's pounds. I'm forgetting my units, I have to admit. I think it's 2 pounds of honeycomb and 2 pounds of alphabets, and by the way, I'm saying these in the backwards order. Alphabets comes first and honeycomb second. So, depending on how the question is phrased to you, you may be asked, what's the most money you can make? Sometimes you're asked, though, how many pounds of alphabets and how many pounds of honeycomb should I make? And if you come back with the answer 14, that doesn't answer the question that I asked. I asked about pounds of alphabets and honeycomb, so I would have to mark down if you made that mistake. Okay, that's it. That's the lesson. Here's the homework assignment. When you come in next class, we'll go over it.